Hello and welcome to the mini test solving of lecture 25, application of derivatives. So here is the mini test for those of you who came to just solve it. And let's get right ahead into process of solving. So we had to approximate the value. Our function is square root of x, and we need to approximate the value at x equals 4.1. So let's write out the formula. So the y value we're searching for is obtained with this. Our x is the value we're approximating for, and our a is a number that's close to it, and that we know how to solve for it. So we need a derivative of our function, we need the value of the function, and the derivative when the a is inserted, and that's about it. Then we basically plug them all into the formula and we're done. So we got our derivative and our function. I reshaped the function into exponent form, and then I used the power rule to get the derivative. Now let's find a good a that's close to 4.1, and that the square root is easy to solve for. And I think 4 would be a great fit. Okay? So now let's insert it into our function and the derivative to get the values and then insert them into the formula. So I fix this for a, so it actually fits into the formula. I insert 4 instead of a. I get 2 for the value of the function and 1/4 for the value of the derivative. So I insert the values in here like that, and then I insert the x and a. I solve it. The difference here is 0.1. 1/4 times 0.1 is 1/4 times 1/10, which is like 1/40th plus 2. So 1/40th equals to 0.025. So adding that to 2 is 2.025. And this is our estimation, which we write something like this. So the square root of 4.1 is approximately 2.025. Now, if I take out my trusty calculator, and let's say 4.1, and then take a square root of that, yes, the actual value is 2.02484. So minus 2.025 divided by 2.025, yeah, times... okay, I don't know, my calculator is messed up. Anyway, but yes, it's very close. This is like a 4 and an 8 after that, so very good approximation. Now, for our second task, we had to find local extrema, meaning finding maximums and minimum. So for that we need its first and second derivatives. So the first derivative is this one, which I forgot to split apart, I guess. So this is the first derivative from the power rule. I factor out 3, and then I break it using the... I forgot the word for it, but basically the binomial expression. No, that's not the one. I know there's a word for this, I forgot it. Anyway, we find the zeros. 0, 1 is... Oh, sorry, x1 is at x is 3, and x2 is at x is 1. Now that we have our second derivative, because I take the power rule of this one again, and the zeros, we insert those zeros into the second derivative. So the second derivative of x1, insert x1, and then the second derivative of x2, insert x2. We get a positive result for the x is 1 for the first x, and the negative result for the second x, which means that the one at x equals 3 is positive, so that's a minimum, while the 0 at x is 1 is negative, and that means it's a maximum. So we do the arrows part, and then x equals 3 and x equals 1. The y at the second derivative is this. This is our minimum, and this is our maximum. Now, we clear out our table, and then we insert these x's into our original function, because we have to find the points. So we get our original function, insert the x's in both of them. And the first one is 1 plus 3, because 1 to the power of 3 is 1. Then minus 6 plus 9 is plus 3. And for the second one, I color-coded it because 3 to the power of 3 is 3 times 3 times 3. 6 can be rewritten as 2 times 3, and 9 can be rewritten as 3 times 3. And then 9 is rewritten as 3 times 3 times 3. So we see 3 to the power of 3, 3 to the power of 3, 3 to the power of 3. These two are positive, and this one has a 2 times that. So if we replace 3 to the power of 3 with like a, so it's a minus 2a plus a, which is 0. So first one adds up to 4, the last one adds to 0. And Now, since we just lost the functions, I color-coded it to make the process easier. Blah, 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 blah. They all cancel out, so our local extrema, so the minimum and maximum, at the point 1,4 we have a maximum in this function, and at point 3,0 we have a minimum, and that's it. That's the solution. Yeah, I think the tricky part here was to know the correct order of solving and to actually solve for the points, because you have to find the local extrema. So maybe the last step is what some of you have forgotten. If you didn't, truly congrats to you for remembering or figuring it out, or just reading and knowing that you have to find the points, not just determine whether the points are maximum or minimums. But yeah, that's it, and let's go to the last one, I think. Yes. Let's first try with direct substitution to find the limit. We insert 0, and we get 0 divided by 0. Let's use L'Hopital's rule, which we by now that is the limit of some function, if the limit of some function divided by the second function equals to 0 divided by 0, we can replace the functions with their respective derivatives. So this is the function 1, this is the function 2, derivative of the function 1, derivative of the function 2. We insert them into this formula. We insert in the x is 0, and we get e to the power of 0 is 1, and we get 1 as the answer. Thank you so much for tuning into the mini test solving. I hope everything went well, and I'll see you all next time. Bye!